Okay, pH. We need to talk about pH, and pH stands for the potential of hydrogen. Remember that an acid is about donating a hydrogen and a base is about accepting hydrogen. So this is why hydrogen comes into play now, and we're looking at concentrations. So, self-ionization of water. Water is self-ionizing. It will react with itself. H2O plus H2O will make H3O positive, which is hydronium, and hydroxide, OH negative. It's going to ionize itself to a certain degree. So some of it will act as an acid, some of it will be a base and form the conjugate acid and the conjugate base. This is important for the following reason. Experimentally, it has been found that for dilute solutions at 25 degrees Celsius, the concentration of hydronium or H positive will always, when multiplied by the concentration of hydroxide, will always equal 10 to the negative 14 molar squared. And Kw here is the ionization constant for water. So, at 25 degrees Celsius, in any solution, the concentration of hydronium times the concentration of hydroxide will always equal 10 to the negative 14 molar squared. This is important because now we know if we can work out, or if we know the concentration of hydronium, we can always work out the concentration of hydroxide, or if we know the concentration of hydroxide, we can work out the concentration of hydronium. Okay, so if an acid or a base is added to water, the H plus or OH negative concentration will change. If an acid is added, then the H plus concentration will increase. Remember, acids donate hydrogen ions. If a base is added, then the hydroxide concentration will increase. The reason being, the base will accept a hydrogen and take that away from the water. So when the water loses one hydrogen, it becomes hydroxide. So we can now say that at 25 degrees Celsius, a solution is an acid if the hydronium concentration is greater than the hydroxide concentration. Or another way of saying that is if the hydronium concentration is greater than 10 to the negative 7 and the hydroxide concentration is less than 10 to the negative 7. Remember, 10 to the negative 7, 10 to the negative 7 is 10 to the negative 14. It will be neutral if the hydronium concentration is 10 to the negative 7 and the hydroxide concentration is also 10 to the negative 7. It will be a basic solution if the hydroxide concentration is greater than the hydronium concentration. In other words, the hydroxide concentration is greater than 10 to the negative 7 and the hydronium is less than 10 to the negative 7. pH, as I said, this is talking about, or it stands for potential of hydrogen. And the potential of hydrogen is just basically the concentration of hydrogen ions in a solution or in a substance. And we can work this out via this formula. pH equals the negative log 10 of hydronium. Now don't stress too much if you don't know much about logarithms. All you need to know is how to manipulate these calculations in your calculator, and I can help you with that if you're struggling. Another way, if you rearrange this calculation, you can get this formula. The hydronium concentration equals 10 to the negative pH. pH is an inverse relationship. In other words, the lower the pH, the higher the concentration of hydronium ions. And we already know this because a low pH, pH of 1, 2, 3, 4, 5 or 6, is an acidic solution. The lower the number, the higher or the more acidic the solution is, so the higher the concentration of hydronium ions. So 1 pH unit is actually an increase of 10-fold of hydrogen ions. And that's important to remember, and I'll show you on the next slide because that explains it a bit more easily. So here I've got concentration of hydrochloric acid, and my concentration is 0.1 molar. So when I work out the concentration, it's 10 to the negative 1. So using the formula above, where concentration of hydronium equals 10 to the negative pH. If it's 10 to the negative 1, it's got a pH of 1. I divide this concentration by 10. I now get 10 to the negative 2, and it's a pH of 2. I divide it again by 10. 10 to the negative 3, pH of 3, and so onwards. So if I go from 3 to 4, I'm actually diluting it by a factor of 10. So the concentration has decreased by a factor of 10. And here's just showing you again that acidic solutions have a high hydrogen concentration, and alkaline or basic solutions have a high hydroxide concentration. And that's just what I was showing you before. So it's just another way of writing it. An acidic solution will always have more hydronium than hydroxide. A basic solution will always have less hydronium than hydroxide. And a neutral solution will always have equal amounts of both of these. This is at 25 degrees Celsius. Okay, so there's 3 formulas you really need to remember. The first one is this, and this is the concentration of hydronium multiplied by the concentration of hydroxide equals 10 to the negative 14. The second one is that pH equals negative log 10 hydronium concentration, and the third one is that the hydronium concentration is equal to 10 to the negative pH. I'm going to do a couple of examples now for you. So first question here, calculate the hydronium and hydroxide ion concentrations and the pH for a 0.1 molar HCl solution. So the first thing you want to think about is what's happening. So you've got hydrochloric acid, which is a gas. At room temperature, hydrochloric acid is a colourless gas. And we saw this the other day in the fume cupboard when we mixed. Remember Mrs. Toyne came in and we opened up the 2 bottles of the concentrated hydrochloric acid and also the ammonia, and we could see sort of like smoke coming out of the bottle, and that's because concentrated hydrochloric acid at room temperature is a gas. So we mix that with water, which always is a liquid, and hydronium ions, aqueous, plus chloride ions, aqueous. Okay, so it's a strong acid, and by strong acid we know that it pretty much completely ionizes in water. So if I've got 0.1 molar of HCl, I'm going to get 0.1 molar of hydronium ions. So I know that the concentration of H3O positive equals 0.1 molar. We look at our formula now. And we can remember that the concentration of OH negative times the concentration of H3O positive equals 10 to the negative 14. So now we can solve for the OH concentration, which will be OH negative equals 10 to the negative 14 divided by the concentration of H3O positive, and that equals 10 to the minus 14 divided by, what's our concentration here? 0.1. And when we work that out, we get an answer of 10 to the negative 13. The other formula that we need to know is that pH equals log 10 hydronium concentration. So it equals negative 10 of, here's our hydronium concentration, 0.1 molar, which equals 1.0, and that's our pH. Okay, so worked example number 2 here. It's asking you to calculate the hydronium and the hydroxide ion concentrations and the pH for a 0.1 molar sodium hydroxide solution. You should be able to recognise sodium hydroxide as a strong base. So, when sodium hydroxide is put into water, it will dissociate into sodium ions plus hydroxide ions. So you can see from this now that 0.1 molar of sodium hydroxide will create 0.1 molar of hydroxide ion concentration. So we've worked out the hydroxide ion concentration. Now we need to work out the hydronium ion concentration. And the way in which we do this is by using the formula hydronium ion concentration times hydroxide ion concentration equals 10 to the negative 14. And this will always be the situation. So now all I need to do to find out my concentration of hydronium ions is hydronium ion concentration will equal 10 to the negative 14 divided by my hydroxide ion concentration, which equals 10 to the negative 14 divided by 0.1, which equals 10 to the negative 13 molar. Okay, last thing left to find out is to work out pH. Two ways to work out pH. First one I'll show you is pH equals negative log 10 of hydronium ion concentration, which equals negative 10 of what we've just worked out here. So it is 10 to the negative 13. So 10 to the negative 13 which equals, or the other way, which I find easier myself to do it, is the formula hydronium ions equals 10 to the negative pH. If you use this one, you can put in that it equals 10 to the negative 13, which again, I just got that information from up here. But have a look now. You can see here 10 to the negative pH, 10 to the negative 13. So that should be quite clear then that pH equals 13. Okay, so worked example number 3 here. If you're feeling confident, have a go yourself. Just pause this for a minute and have a go on a separate piece of paper. Okay, so it's asking you to calculate the hydronium ion, the hydroxide ion, and the nitrate ion concentrations in a solution of nitric acid with a pH of 3.0. So we need to go backwards with this calculation. We know that we have nitric acid, which, when put in water, will fully ionize into hydronium ions plus what's left in nitrate ion. So looking at the question already, we can see that we've got a pH of if we put that into the calculation, H2O positive equals 10 to the negative pH, which equals 10 to the negative 3, we get a concentration of hydronium of being 0.0010 molar. Excellent. So that's the first part of the question sorted. The next bit's asking you for the hydroxide concentration. So we need the calculation of H3O positive times OH negative equals 10 to the negative 14. So our OH concentration will be equal to 10 to the negative 14 divided by concentration of your hydronium, which equals 10 to the negative 14 divided by 10 to the negative 11, negative 3, I beg your pardon, which equals 10 to the negative 11. Just note, in your questions, this is the wrong answer. I think they've got 10 to the negative 1 is the answer, but that is incorrect. It's 10 to the negative 11. Okay, have a look back at the equation, and it's a 1 to 1 to 1 to 1 ratio. Thus, the concentration of nitrate has to be equal to the concentration of hydronium, which equals 0.001 molar. So that is the concentration of your nitrate ion. Last thing to talk about is indicators. Acid-base indicators are mixtures of a weak acid and its conjugate base. The acid and the conjugate base forms are different colours, and that's how an indicator works. And the best way of looking at it is this diagram here. Take a look at this middle picture here first. So this is your indicator in water, and what you have is a combination of the acid, which is a weak acid, and that weak acid's conjugate base. Remember, a conjugate base of an acid is just one hydrogen ion less. And that's what you have here. So you have HA, which is the weak acid, and A minus, which is its conjugate base. If we put this indicator into a base, what will happen is all of these weak acids in the indicator will donate their hydrogens, and it will leave us with lots and lots of the conjugate base, which is this lighter yellow colour here. If, on the other hand, we place this indicator mixture into an acid, all of these A minuses, which are the conjugate base, or acting as a base, will accept a hydrogen. And so you will get a solution full of HAs, which are this darker orangey colour. That's the way that all indicators work. They're mixtures of weak acids and its conjugate base. So they'll either become bases when they're put into acids, or they'll become acids when they're put into bases. Okay, so different colours depending on what sort of indicator you're using, and they will also show a different range for a colour change, a different pH range. For instance, here you've got methyl orange, and methyl orange is used to find or differentiate between pHs of about 3.5 to 4.5. Litmus paper that we use often is, and then we know that acids go red and bases go blue. Universal indicator. Universal indicator has a rainbow of colours, and that's why it's pretty much called universal, because you can do most of your pHs. Bromothiamyl blue will either be yellow up to about pH of 6.6 or so, and after that it will turn blue. And phenolphthalein is colourless as an acid, but it turns pink in a base, and you'll be using a little bit of this when we do titrations later on. So you've got some questions now on pH calculations that you can start working through, and basically you should be able to finish all of Chapter 14 questions now.